You're team 20.
Okay, yes.
Is the camera set?
Yes, okay. We're team 20 and we're presenting the Intercollegiate Rocket Engineering Competition. So with me is Giancarlo Lombardi, Christopher Hayes, and myself, Maria Gonzalez. So a little bit of the presentation, we will be talking about the competition challenges and goals, followed by the airframe design recovery system, then the propulsion system, and lastly, rapid air brake deployment system. So after that, we will consider the computer simulations, testing and validation that we'll go through, as well as engineering standards, curriculum applications, global learning, and lastly, our team Christopher. Thank you. I'll hand things over to Christopher Hayes now.
Okay. The goal of this competition is to design and construct a rocket capable of carrying a 10-pound payload to 10,000 feet above ground. Mostly, with most parts constructed by ourselves and fabricated by ourselves. Okay, so we've separated our systems into four different systems: the propulsion system, the recovery system, airframe, and the altitude targeting system. And below you can see our focus for each system. For propulsion, it's a simple design, and we're trying to get for the highest thrust to weight ratio possible. Recovery system, we're using dual deployment, and we just want to focus on reliability and redundancy. For our airframe, again, it's just mostly lightweight design and just aerodynamic performance. And our altitude targeting system, we're actually using an air brake system, which will be deploying parachutes on the way up to try to reach 10,000 feet exactly. Okay, so like airframe, I said before, we're focusing on strength and material choice. So most of our options there are just different materials, whether it be carbon fiber, aluminum, fiberglass. We're going to have to evaluate all of those. Stability is the center of pressure versus center of gravity, and we want to make sure we're stable with our design. And our structural integrity is the bulkheads, fins, and centering rings, what we construct them out of, as well as their shape and design. Okay, so our propulsion system, we're evaluating three different systems, our designs, the solid, the liquid motor, and the hybrid motor. Okay, so here's a basic overview of each one. For the solid motor, it's basically just solid grain stacked inside a tube, and you light it off, and it just burns without any control. It burns until it's done. For the hybrid motor, you have a solid grain in the combustion chamber, separated by an injector bulkhead, and then an oxidizer tank on top, which will be mostly nitrous oxide. And then that will spray in and combust with the solid grain. The liquid engine that we have here is actually a unique design. Basically, the nitrous oxide will pressurize the liquid fuel and inject both into the combustion chamber. And okay, that's pretty much it. So the advantages and disadvantages of each system that we're evaluating. For the solid motor, it's the simplest design. It's also risky because it has the larger you go, the greater the chance that it actually did blow up. It's also high powered, and it's also very expensive to buy a new solid motor each time. For the hybrid motor, it's the lower power of the three, but it's also low cost over time, and it's a simple design. The liquid motor is extremely complex and high cost. So which one we're thinking about going with so far is hybrid motor.
So our next system that we will implement for this competition, and it's critical for the operation of the rocket, is recovering it safely after launch. So our conventional method that is used in practice in the field of hobby rocketry and high-powered rocketry as well is dual deployment. And essentially what this is you have a drogue parachute, a really just small parachute that gets ejected at apogee, your highest point of flight, such that on descent your rocket cannot attain a ballistic profile, and it gets destabilized. And then at a much lower altitude, we will deploy essentially what's called the main parachute, and really all that is just a big parachute to slow you down. In order to control the deployment of each parachute, we will be buying a commercial flight altimeter that's they're very reliable, and we have used them in previous projects. And as with the airframe, the focus will be placed on the structural elements such as the bulkheads, the eye bolts, and shock cords attached to the parachutes due to the high impact on deployment. So then, the competition requires us to attain an altitude as close to 10,000 feet. That would be the scoring rubric for this competition. In order to effectively target this altitude, we'll be deploying 2 parachutes on the coast up. So after motor burn, we will be programming the altimeter. It has a built-in IDE where we will essentially employ basic drag equations and kinematic equations such that we'll know exactly the distance needed based on the parachute dimensions and characteristics, the distance needed to reach the 10,000 foot mark. Essentially what the system will comprise of is 2 external parachutes that will be connected to the flat altimeter. The center electronics bay up here and slow it down on the coast up. So in order to verify our systems, our preliminary analysis will be conducted in a commercial software called RockSim. What this software allows you to do is essentially create all your structural components of the rocket as and integrate it next to each other. And what this gives you directly is the center pressure and center of gravity given your motor choice, such that we will, out of basic understanding, know the aerodynamic performance. And then once you select your motor, you can also attain your flight profile with all the events as parachute deployment and that we need. So moving on, once we know that our design will have aerodynamic stability, we'll move on to Solidworks, where we'll model, and this will verify the geometry such that all the parts will fit with each other. And we'll simulate using structural and external flow. And this will essentially be used as before testing, the final step where we can verify that everything will work. And we'll be using ANSYS as a redundancy to verify that everything is in order. So then, once after having constructed the rocket, we'll move. Some conventional testing methods that we'll employ is a static fire test and a ground ejection test. The static fire test, since we are going to buy a commercial motor, we just, if we were to ignite it and use it, there would be a high chance that it would work, but we just want to verify that everything is in order and we have the proposed motor thrust curve. And an airframe structure test will be employed due to our selection of material. We want to verify that at our tube diameter and length that the strength of the material will surpass the expected loads. And some more tests that we will employ is a ground ejection test, and this is done conventionally in the high-powered rocketry field, where you essentially prepare the rocket for flight, and using your black powder charges, you simulate the pressure at a certain altitude and ensure that there will be perfect separation of rocket components to deploy the parachute. And we'll also be using this method to test our air brake system deploying parachutes. I will now pass it back to my teammate, Marielle.
So just to finalize everything, the curriculum applications will be fluid dynamics, gas dynamics, where the supersonic speeds, compressible fluids, as well as the nozzle design will be validated. As also mechanics and materials, where materials to be selected, such as the composites and metals that were aforementioned, will be tested for structural integrity and of the rocket during its flight. Okay, so some engineering standards observed are the NAR High Power Safety Code, since we are launching the rocket. So National Fire Protection Association Code for High Power Rocketry, Chapter 2. The Federal Aviation Administration Code for Federal Regulations, Part 101, Subsection C, which is basically just rockets. And the Federal Explosives Law Regulations, Part 555, and the Anti-Machinery Safety Standards when we need to lay certain parts. So global learning aspects, we want to go towards a cost-effective approach for manufacturing and assembly, considering that we're students and we don't really have research and funding. And we want to maximize access for the public, so this can be implemented for other countries or other students' projects. And of course, the strict adherence to established codes and standards. We want to have safety for our personnel. And lastly, we want to use SI and English units for all simulations and all designs. And this is our poster. So thank you very much.
Any questions, please?
What is the size of this, the scale? I mean,
So conventionally, we've worked on other projects, and basically we're given the weight and expected altitude. This will probably be attaining up the height of maybe 9 feet and a tube diameter of like 6 inches.
For us, it's going to be anywhere from like 400 pounds to up to 1,000 pounds.
Where are you launching this? Where is the competition?
The competition is actually in Utah.
And there's salt flats.
And we could actually do test launches on the same size in the Orlando area. They have waivers up to 10,000 feet.
Right, so for testing and everything pre-competition will be, there's a club launch located in Gwinnett, Florida, it's just above Orlando. And then the actual competition will be located in the Salt Flats in Utah. Yeah.
Can you guys talk about, you have 3 different motor design choices, right?
Yes.
So what will be the parameters that you're going to change in each of those 3, and what will you be looking to get in the outcome when you do that?
Well, we're going for bot motors are commercially available, and so we really want to just find one that can actually overshoot our altitude a little, so the altitude targeting system works. We probably don't want to go with the higher thrust ones because we don't want to go above Mach, which will just create more drag and less efficiency. If we buy a hybrid, we're thinking about going hybrid because it's the most I guess
It's the most reliable.
And we could customize that because if we do need a different combustion chamber, we can make our own combustion chamber and nozzle and switch out that if the one that is from the store or whatever doesn't work for us. As well as the fuel grade, we can change out that.
So I saw the diagram of the parachutes, right?
Yes.
So the whole point is to get to 10,000 feet as close as possible. So
Yeah.
however you get there and brake, right? That's to make sure you don't burn those parachutes, number one, right?
Right. No. Yeah, it will be completely off motor for us by then. The motors usually, I mean, we're probably looking at maybe like a 6-second burn or something like that, I'd estimate. And
and they just by this inertia, it was.
Yeah, it would probably travel the last 2,000 or 3,000 feet without just momentum.
Can you get penalized if you go past 9,000?
Yeah.
Over or below, the closest to 10,000 is the most points. We're allowed to actually go over by 200 feet, I think, without actually being like disqualified.
Have you considered maybe deflection plates?
Well, actually, other teams have done that, and they haven't worked very well. Because, I mean, when you have the small plates, you're not really creating too much drag, so it's kind of hard to balance it out. We're just going with like we know it's going to work, and we know it's going to work at that distance.
What kind of interior? I may have lost that. You probably said the actual tubes themselves.
So conventionally, what you're looking for is a high strength, low weight for aerospace applications. So we're looking at either carbon fiber, or if we need to move on to a stronger material, ductile metal like aluminum. But we're going to start our analysis phase before we begin anything with carbon fiber, just to ensure that we don't need to have that excess strength, essentially. Yeah.
Or fiberglass.
Yeah, you may have mentioned, I just happened to miss it.
Okay.
I'm thinking, what are they making it out of?
Yeah, that's right.
And different sections might be made out of different things as well.
All right, thank you very much. Appreciate it. Before